Hello, in today's lesson, we're going to dive deep into some of the most powerful and elegant methods for analyzing complex electrical circuits. By the end of this video, you will be able to apply these techniques to solve almost any linear circuit you encounter. Specifically, our learning objectives are to master two fundamental techniques: the mesh current method and the nodal voltage method. We'll also cover several related but equally crucial concepts that simplify circuit analysis even further. These include Thevenin's and Norton's theorems, maximum power transfer, superposition, and source transformations. These methods aren't just academic exercises. They are the bread and butter of electrical engineers, making the analysis of intricate circuits manageable. Think of them as your toolkit for breaking down a complex problem into simpler, solvable parts. Let's get started with our first powerful tool. Our first method is the mesh current method. This technique is especially useful for circuits that can be drawn on a flat surface without wires crossing, a type of circuit we call a planar circuit. The core idea is to apply Kirchhoff's voltage law, or KVL, around the loops in the circuit. But there's a specific way we do it. We identify what are called meshes. A mesh is essentially a window in a planar circuit. It's a loop that doesn't contain any other smaller loops inside it. Imagine the circuit as a series of windows. Each one of these is a mesh. For example, in this simple circuit, we can see two distinct meshes, or loops, that don't overlap. Our first step, therefore, is to identify and assign a unique mesh current to each mesh. We'll assign a clockwise direction to these currents by convention. Let's use our example. We have two meshes. We'll assign a clockwise current, which we'll call I1, to the first mesh. And we'll assign another clockwise current, I2, to the second mesh. Remember, these are theoretical currents that flow around the mesh. The actual current in any branch of the circuit will be a combination of the mesh currents flowing through it. In the middle branch, for instance, the actual current is the difference between I1 and I2. Once we've defined our mesh currents, the next step is to write a Kirchhoff's voltage law equation for each mesh. This means that for each mesh, the sum of all the voltage changes as you trace around the loop must be 0. Let's do this for our circuit. Let's start with mesh 1. We'll add some components to make our example concrete. Let's say we have a voltage source, V1, a resistor, R1, and a central resistor, RC. As we trace clockwise around mesh 1, we first encounter the voltage source V1. Since we're going from negative to positive, it's a voltage rise, so we'll call it positive, plus V1. Next, we go through resistor R1. The voltage drop across R1 is its resistance times the mesh current flowing through it. In this case, only I1 flows through R1. So we have minus I1 times R1. Finally, we go through the central resistor RC. Now this resistor is part of both meshes. The voltage drop across it is determined by the net current flowing through it in our tracing direction. From our perspective in mesh 1, I1 flows down and I2 flows up. The net current in our downward direction is I1 minus I2. So the voltage drop is minus the quantity I1 minus I2 times RC. We've completed the loop, so we set the sum to 0. And that's our Kirchhoff's voltage law equation for mesh 1. We would repeat this exact process for mesh 2, creating a second equation. We'll do that in a full example in the next scene. Now let's apply the mesh current method to a full worked example. Suppose we want to find the current flowing through a 4-ohm resistor in this circuit. The circuit has a 12-volt source, a 6-volt source, and 3 resistors: 2 ohms, 3 ohms, and 4 ohms. Our first step is to identify the meshes. We can see 2 clear, non-overlapping loops. Next, we assign a clockwise mesh current to each mesh. Let's call the left current I1 and the right current I2. So we have I1 flowing through the left loop and I2 flowing through the right loop. Now we write a KVL equation for each mesh. For mesh 1, starting from the 12-volt source and going clockwise, we get plus 12 volts, minus 2 ohms times I1, and minus the net current through the 4-ohm resistor, which is I1 minus I2 times 4 ohms. All of that equals 0. Let's simplify this equation. Distributing the 4 gives us 12 minus 2i1 minus 4i1 plus 4i2 equals 0. Combining the I1 terms, we get 12 minus 6I1 plus 4I2 equals 0. We can rearrange this to get our first clean equation. 6I1 minus 4I2 equals 12. Now let's do the same for mesh 2. Starting from the 6-volt source, we trace clockwise. This gives us minus 6 volts, minus 3 ohms times I2, and minus the net current through the 4-ohm resistor, which is now I2 minus I1 times 4 ohms equals 0. Simplifying mesh 2, minus 6 minus 3I, 2 minus 4I, 2 plus 4I1 equals 0. Combining terms, we get minus 6 plus 4I1 minus 7I2 equals 0. Rearranging gives us our second equation. 4I1 minus 7I/2 equals 6 and I2. Now we have a system of two linear equations with two unknowns. We can solve this using any method we like, such as substitution or elimination. Using a solver or by hand, we find that I1 is approximately 2.57 amperes and I2 is approximately 0.57 amperes. The question asked for the current through the 4-ohm resistor. This is the net current I1 minus I2. So 2.57 minus 0.57 gives us 2 amperes. And that's how we solve a two-mesh circuit. There's a special case in the mesh current method called a supermesh. A supermesh is created when a current source is located on the boundary between two meshes. Let's look at this circuit. We have two meshes, but between them is a current source. Let's say 3 amps. This current source creates a problem for our standard KVL equation because the voltage across a current source is unknown. To solve this, we create a supermesh. A supermesh is formed by combining the two meshes that share the current source. Think of it as cutting out the current source and the branch it's on, and then treating the remaining larger path as a single mesh. So, we'll draw a larger path, encompassing both loops but skipping over the current source. This is our supermesh. We now write a single KVL equation for this supermesh. For our example, if the outer components are V1, R1, R2, and V2, the supermesh equation would be V1 minus I1R1 minus I2R2 plus V2 equals 0. Notice it includes components from both original meshes. This gives us one equation, but we have two unknowns, I1 and I2. We need another equation. This second equation comes from the current source itself. Looking at the current source, we see that it defines the difference between the two mesh currents. If the source flows in the same direction as I2 but opposite to I1, our constraint equation is I2 minus I1 equals 3 amps. Now we have a system of two equations and two unknowns, and we can solve it just like before. So, a supermesh simplifies the problem by removing an unknown voltage and replacing it with a constraint on the currents. Now let's move on to our second major technique, the nodal voltage method. While mesh analysis is based on KVL, nodal analysis is based on Kirchhoff's current law, or KCL. The fundamental principle is that the sum of all currents entering and leaving a junction, or node, must be 0. This is a statement of charge conservation. Current can't just appear or disappear. A node is any point where two or more circuit components are connected. Just like we defined meshes, the first step in nodal analysis is to define our nodes. In this circuit, we have 4 distinct nodes. 1 on top, 1 in the middle, and 2 on the bottom. Our goal is to find the voltage at each of these nodes relative to a reference point. This brings us to the second and arguably most important step, choosing a reference node. We must select one node in the circuit to be our reference, or datum, and we define its voltage to be 0. This is often called ground. By doing this, the voltage of any other node, let's call it Vn, is simply the potential difference between that node and the ground node. The best strategy is usually to pick the node that has the most connections to simplify your math. After choosing the ground, we label the voltages of all other nodes as our unknown node voltages. For example, VA, VBB, VC, and so on. We now have a set of variables we want to solve for. With our nodes and reference defined, the next step is to write a KCL equation at each essential or non-reference node. An essential node is one that connects 3 or more components. The process is always the same. We assume that all currents leaving the node are positive. The sum of these currents must equal 0. Then we express each of these currents using Ohm's law. Let's take a closer look at our example circuit. Let's say we have two essential nodes, labeled A and B, and we've set the bottom node as ground, VG equals 0. We also have a voltage source, Vs. Let's write the KCL equation for node A. We'll assume three currents are leaving the node. The current leaving through R1 is the voltage drop across it, which is VA minus the source voltage, divided by R1. The current leaving through R2 is VA minus the ground voltage, which is 0, divided by R2. So VA divided by R2. And the current leaving through R3 is VA minus the voltage at node B, divided by R3. We sum these three expressions and set them equal to 0. This is our first nodal equation. We would then do the same thing for node B. This gives us a system of linear equations that we can solve for our unknown node voltages, VA and VB. Let's work through a concrete example of nodal analysis. We want to find the voltage across the 4 ohm resistor in this circuit. First, we identify our nodes. We have two non-reference nodes. We'll label them A and B. We'll set the bottom node as our ground, VC equals 0. So our unknowns are the node voltages VA and VB. Now let's write the KCL equation for node A. Remember, sum of currents leaving equals 0. The current leaving through the 2 ohm resistor is VA minus 10, divided by 2. The current leaving through the middle branch is a 2 amp current source flowing in, so the leaving current is negative 2. The current leaving through the 4 ohm resistor is VA minus VB, divided by 4. Let's simplify this. We can multiply the whole equation by 4 to clear the denominators. That gives us 2 times VA minus 10 minus 8 plus VA minus VB equals 0. Expanding, we get 2 VA minus 20 minus 8 plus VA minus VB equals 0. Combining terms, our first nodal equation is 3VA minus VB equals 28. That's our first equation. Now for node B. The current leaving through the 4 ohm resistor is VB minus VEA divided by 4. The current leaving through the 6 ohm resistor is VB divided by 6. And we have a 5 amp current source leaving, so it's plus 5. Simplifying node B. Multiply by 12. That gives us 3 times VB minus VA plus 2VB plus 60 equals 0. Expanding gives 3VB minus 3VA plus 2VB plus 60 equals 0. Combining terms, we get minus 3VA plus 5VB equals minus 60. Let's rewrite this as 3VA minus 5VB equals 60. Now we have our system of two equations. We can solve these by elimination. Notice the 3VEA term. If we add equation 1 and equation 2 together, the 3VEAs cancel out, leaving us with minus 4VGB equals minus 32. This means VB must be 8 volts. Plugging this back into equation 1 gives us 3VGA minus 8 equals 28, so 3VEA equals 36, and VA equals 12 volts. Wait, I made a mistake. Let's trace back. In node B, I multiplied the 5 by 12 to get 60, but it was a plus 5. So the rearranged equation should be 3V 5VB 60, or 3V 5VB 60. Now let's try again. 60. Now let's try. If we subtract the second equation from the first, we get 4VB equals negative 32. So VB is negative 8 volts. Plugging that into the first equation, 3VA plus 8 equals 28. So 3VA equals 20, and VA is 20.3 volts, or approximately 6.67 volts. Now the question was the voltage across the 4 ohm resistor. This is the difference between the voltages at its two terminals, which is VA minus VB. That's 23 minus negative 8, which is 23 plus 243, for a total of 44.3 volts. That's our answer. This example shows that even experienced analysts can make mistakes, and checking your work is key. Similar to the super mesh, nodal analysis has a special case for voltage sources called a supernode. A supernode is formed when a voltage source, whether independent or dependent, is connected between two non-reference nodes. In this situation, the voltage source makes it impossible to define the current leaving the node without introducing new unknowns. To solve this, we create a supernode. This involves treating the entire region enclosed by the voltage source and the two nodes it connects as a single larger node. We can imagine the voltage source shrinking to zero, effectively merging the two nodes together. We then apply KCL to the terminals of this combined supernode. The key is that the sum of all currents entering and leaving this entire region must be zero. This gives us one equation. But just like with the supermesh, we need a second equation. This comes from the voltage source itself. The voltage source explicitly defines the difference between the voltages of the two nodes it connects. So we have a constraint equation. For example, if the source is oriented to make node A positive with respect to node B, the constraint equation would be VA minus VB equals Vx. Now you have a system of two equations, a KCL equation for the supernode and a constraint equation from the voltage source. You can solve these for the unknown node voltages. The supernode method cleverly handles the voltage source by treating it as a constraint, making the circuit solvable with standard KCL. So which method should you use, mesh or nodal? It's a great question, and the answer is that it depends on the circuit. The mesh current method is generally easier when a circuit has fewer meshes than non-reference nodes. The number of meshes is just the number of windows. The number of nodes is found by taking the total number of nodes, including the reference node, and subtracting 1. The goal is always to have the smallest number of equations to solve. Fewer equations means less work and fewer chances for mistakes. A circuit with a lot of junctions, or nodes, but that's very simple in structure and has only 2 or 3 meshes, is a good candidate for mesh analysis. Think of a simple ladder network. Conversely, a circuit with many loops but only a few key junctions or nodes is often better suited for nodal analysis. A good example is a bridge circuit. Both methods are equally valid for linear circuits, and both will give you the same correct answers. The best choice is the one that simplifies your work. With practice, you'll develop an intuition for which method to choose. Now let's explore some theorems that allow us to simplify circuits even further. We're now going to explore a family of incredibly powerful theorems that allow us to simplify complex circuits, making them much easier to analyze. We'll start with source transformation. The source transformation theorem states that any independent voltage source in series with a resistor can be transformed into an equivalent independent current source in parallel with the same resistor. And the reverse is also true. Let's see what that looks like visually. If you have a voltage source, VSS, and a resistor, R, in series, you can replace the entire setup with a current source, ISS, in parallel with that same resistor, R. The relationship between those equivalent sources is given by Ohm's law. The current of the equivalent source is simply the voltage of the original source divided by the resistance, VSR, and of course, VSE R for the reverse transformation. Why is this useful? Because it can dramatically simplify a circuit. Imagine a circuit with a voltage source and a resistor in series, right next to a parallel branch. By transforming the voltage source, you create a current source that's now in parallel with other components, allowing you to combine them and reduce the number of components. It's all about making your life easier by transforming the circuit into a more convenient form for either mesh or nodal analysis. Let's put source transformation into action with an example. Suppose we want to find the current through the 3 ohm resistor in this circuit. Looking at the circuit, we see 2 voltage sources. Let's analyze the left branch first. We have a 24-volt source in series with a 4 ohm resistor. This is a perfect candidate for source transformation. Using Ohm's law, the equivalent current source is 24 volts divided by 4 ohms, which is 6 amps. The equivalent circuit in this branch is a 6 amp current source in parallel with the 4 ohm resistor. Now let's do the right branch. We have a 6-volt source in series with a 2 ohm resistor. The equivalent current source is 6 volts divided by 2 ohms, which is 3 amps. This gives us a 3 amp source in parallel with a 2 ohm resistor. By transforming the 2 outer branches, we've created a circuit where all 3 main branches are in parallel. We now have a 6 amp source, a 3 ohm resistor, and a 4 ohm resistor all in parallel, plus a 3 amp source and a 2 ohm resistor in parallel. We can simplify this further. We can add the parallel current sources. 6 amps plus 3 amps gives a single 9 amp source. And we can combine the parallel resistors. 1/4 plus 1/3 gives 7/12. The equivalent resistance is 12/7 ohms. So our circuit has simplified down to a single 9 amp source in parallel with a 12/7 ohm resistor. We can use the current divider rule to find the current through our original 3 ohm resistor. The current through the 3 ohm resistor is 9 amps times the equivalent resistance, 12/7 divided by 3 ohms. This gives us 36/7 amps, or approximately 5.1 phoamps. That's the power of source transformation. Next up is the superposition theorem. This is a wonderfully intuitive and powerful theorem that helps us handle circuits with multiple independent sources. The superposition theorem states that in any linear circuit, the total voltage or current at any point is the algebraic sum of the voltages or currents produced by each independent source acting alone. In other words, if you have a circuit with, say, 3 sources, the theorem says you can find the contribution from the first source, then the contribution from the second, then the third. Add those contributions together, and you have your answer for the full circuit. The key phrase here is acting alone. To ensure only one source acts, you must turn off all other independent sources. But what does it mean to turn off a source? To turn off a voltage source, you replace it with a short circuit, or a wire. This sets its voltage to 0. To turn off a current source, you replace it with an open circuit, which sets its current to 0. So the process is, for each independent source in the circuit, you turn off all the others. You calculate the quantity you're interested in, a voltage or current, for that single source. You repeat this for all sources. Finally, you add up the results. Let's see it in action. Let's use superposition to find the current I0 in this circuit. The circuit has a 12-volt source and a 3-amp current source. We'll find the contribution from each source separately and then add them up. First, let's find the current Is prime due to the 12-volt source acting alone. This means we must turn off the current source. We replace the 3-amp current source with an open circuit. This effectively eliminates the right loop, leaving us with a simple series circuit. The total resistance is 1 plus 4, which is 5 ohms. The current I0 prime is just 12 volts divided by 5 ohms, or 2.4 amps. Notice the direction we assumed for I0 matters. Next, let's find the current IO double prime due to the 3-amp source acting alone. This means we must turn off the 12-volt source. We replace the 12-volt source with a short circuit. Now we have a circuit where the 3-amp current is flowing into a junction that splits between the 1 ohm resistor and the 4 ohm resistor. This is a current divider problem. To find I double prime, we use the current divider formula. I0 double prime equals 3 amps times 1 ohm divided by the sum of the resistances. 1 plus 4. This gives us 0.6 amps. Now, our original I0 was defined as downward, but this current is flowing upward, so we must treat it as negative, 0.6 amps. Finally, we add the two contributions together to find the total current I0. I0 is I0 prime plus I0 double prime. That's 2.4 amps plus negative 0.6 amps. Our final answer is 1.8 amps. Superposition allows us to solve a seemingly complicated circuit by solving two much simpler ones. Now let's move on to two of the most famous and incredibly useful theorems in circuit analysis, Thevenin's and Norton's theorems. These theorems, proposed by French telegraph engineer Léon Charles Thevenin and Bell Labs engineer Edward L. Norton, allow us to simplify any complex linear circuit down to a simple two-component equivalent. Specifically, Thevenin's theorem states that any linear two-terminal circuit can be replaced by an equivalent circuit consisting of a single voltage source and a single series resistor. Imagine a complex, unknown circuit inside a box with just 2 wires sticking out. Thevenin's theorem says that from the perspective of whatever is connected to those 2 wires, the circuit behaves exactly like a single, simple voltage source in series with a resistor. Norton's theorem is a dual of Thevenin's. It states that the same linear two-terminal circuit can be replaced by an equivalent circuit consisting of a single current source and a single parallel resistor. So you can choose whether you want to represent the box's behavior with a voltage source and series resistor, or with a current source and parallel resistor. The beauty is that the resistor in both equivalents, Rth of the eth, is the same. It's called the Thevenin or Norton resistance. Also, since these are just different forms of source transformation, you can convert between them using Ohm's law. Vth equals In times Rth. These theorems are revolutionary because they allow you to separate a complex circuit into two parts, the source part and the load part. You can analyze the source part once to get its Thevenin or Norton equivalent, and then you can connect any load to it and quickly see its behavior, without reanalyzing the entire circuit every time. Let's walk through the steps to find a Thevenin equivalent circuit. We'll use the same circuit we analyzed with superposition to find the Thevenin equivalent looking from the terminals of the 4-ohm resistor. Our goal is to reduce everything to the left of these terminals into a Thevenin voltage source, Vth, and a Thevenin resistance, Rth. Step 1. Find the Thevenin resistance, Rth. To do this, we turn off all independent sources in the original circuit. We replace the 12-volt source with a short circuit and the 3-amp source with an open circuit. Then we find the equivalent resistance looking back into the terminals A and B. Looking into the terminals, we see that the 1-ohm and 6-ohm resistors are now in parallel. The equivalent resistance, Rth, is 1 times 6 divided by 1 plus 6. That's 6/7 ohms. So Rth is 6/7 ohms. Step 2. Find the Thevenin voltage, Vith. Thevenin voltage is defined as the open circuit voltage at the terminals A and B. We reconnect our sources but open the terminals. We need to find the voltage VAB. Since the terminals are open, no current flows through the 6-ohm resistor. This means the voltage VAB is the same as the voltage across the 1-ohm resistor. We can use superposition again to find this voltage. With the 12-volt source on and 3-amp source off, the voltage across the 1-ohm resistor is 12 volts divided by 1 plus 1, or 6 volts. With the 3-amp source on and 12-volt source off, the circuit is a current source into parallel 1 and 1 ohm resistors. The current splits, so 1.5 amps flows through the 1 ohm resistor, creating a voltage of 1.5 volts. Adding these up gives a total open circuit voltage, and thus Vth of 7.5 volts. Our final Thevenin equivalent circuit is a 7.5 volt source in series with a 6/7 ohm resistor. Now, if you wanted to find the current through the 4 ohm resistor, you'd just add the 4 ohms to Rth and divide into Vth. So now we have a circuit's Thevenin equivalent. A powerful application of this is the maximum power transfer theorem. This theorem answers a very practical question. Under what conditions will the most power be delivered from a source to a load? It's a simple answer. Maximum power is delivered to a load when its resistance, RL, is equal to the Thevenin resistance of the source circuit, Rth. Think of it as impedance matching. This might seem counterintuitive at first. If the source resistor, Rth, is large, it seems like setting RL equal to it would waste a lot of power in Rth. And that's true. The theorem doesn't say that the transfer is 100% efficient at maximum power. It says that for a fixed source resistance Rth, the maximum power that can be delivered to an adjustable load, RL, occurs at this specific matching point. You can prove this using a bit of calculus. The power in the load, PL, is I squared times RL. If you express the current I in terms of Vt, Rth, and RLCEL, you get Vth squared times RL, all divided by Rth plus RL squared. If you take the derivative of this power equation with respect to RL and set it to 0, you'll find that the function's maximum occurs exactly when RL equals Rth. This theorem is incredibly important in applications like power amplifiers, antennas, and communication systems, where maximizing the power delivered to a load is often a primary goal. Okay, let's wrap this up with a quick recap and a final challenge. Today, we've armed you with a powerful toolkit for analyzing circuits. We started with the fundamentals, KVL and KCL, and then applied them in the structured, systematic approaches of mesh and nodal analysis. We learned how to handle special cases like supermeshes and supernodes, and how to choose the most efficient method. Then we moved to simplification theorems, source transformation to change circuit elements for convenience, superposition to break complex circuits into simpler ones, and finally, Thevenin's and Norton's theorems to reduce any linear circuit to its simplest equivalent form, which also allowed us to understand maximum power transfer. The key to mastering these concepts is practice. So here's a challenge problem for you to try. Your task is to find the current I through the 2 ohm resistor using any of the methods we discussed today. Pause the video and give it a shot. I recommend trying more than one method, and here's the solution. No matter which method you chose, if you worked through it correctly, you should arrive at the same answer. Thank you for joining me today. Keep practicing, and you'll be a circuit analysis pro in no time.